So, electrostatic potential, as we said, we can get a lot more utility out of that than we did gravitational potential. If we look at a point a distance r away from a point charge q, the potential is fairly simple. It's just that constant from Coulomb's law, k, times q over r. If we want to see how all these things fit together, we can put them in this square arrangement where we have force, and it's connected to field by a factor of q. We divide by q or multiply by q to go between force and field. Over here, potential energy, kqq over r, is connected to potential, again by dividing by charge or multiplying by charge. How are these things left and right connected to each other? Really, the easiest way to do it is calculus and say they're integrals or derivatives of each other. But since we can't use calculus, we can say the slope of the potential energy curve gives us the force, or the area under the force curve gives us the potential energy. Same down here, the same connection between field and potential, slope of the curve versus area of the curve. It might be worth writing down the gravitational version of this, the final one that you would have used at the end of Physics 1, where we have the force and the potential energy. The slope of the potential energy curve, again, gives us the force, or the integral of the force with respect to distance. The area under the curve of force with respect to distance is potential energy. If we divide force by mass, we get field. If we multiply field by mass, we get force. Same thing over here with gravitational potential energy and this gravitational potential thing that, as I said, we really don't use. To make it a little bit easier, if we were doing this for the uniform field in the first few weeks of Physics 1, then we would have our force is just mg, our potential energy curve is mgh, the slope of that curve is the force, the area under the force curve is potential energy. Then our field becomes just g, and our potential, which we didn't use, would be just gh. So the field is telling us what force a particular mass or charge would feel if it were present. The potential tells us about the potential energy it would have if it were present. The electrostatic potential comes up so often that we have a little bit shorter name for it. We call it voltage. If you get confused, the thing to remember is you can think of voltage as being a lot like height. First of all, it only makes sense to talk about the voltage between 2 points, just like it only makes sense to talk about the height or distance between 2 points. A lot of times we'll leave off what the other point is if it's obvious. If we're talking about a person's height, we all know we mean the floor is our 0 point, and we're just looking at the height of the other point above that, and a lot of times we'll leave that out. On Earth, most elevations are referenced to sea level, so if somebody told you the height of Savannah was 10 meters, you'd know they meant relative to sea level. However, we can't ignore this completely. If we just hold up one end of a tape measure to measure something, that doesn't mean we're really doing it. The other end has to be in a particular place. For example, in this picture, you can see the 10-foot tape measure mark at the top of this dog's head. The dog is obviously not 10 feet tall. I didn't pay any attention to where I put the bottom of the tape measure, which would make it useless. Same idea, here we have a multimeter, which is like our yardstick for voltage. It has 2 probes, and we have to connect both of them to something if we want it to mean anything. Right now, the red probe is connected to one end of this 6-volt battery. The black probe isn't connected to anything. The display reads something like negative 10.5 millivolts. The reason is that we're not really measuring anything here if we're only connecting one end, just like nothing in this picture is really 10 feet. If we connect the other terminal of the battery to this black probe, then it would read something like 6 volts, which is what we get when it's new. Voltage is a potential energy per charge, so the units would be joules per coulomb. This is so common that 1 joule per coulomb has been defined as a volt, which is, of course, capitalized since it's from somebody's name. A lot of times you'll hear people who don't know physics very well talk about voltage going through something. If someone gets electrocuted, they'll say 10,000 volts went through someone. This doesn't make any more sense than if someone falls off a building, you don't say 100 meters went through the person. You can talk about the voltage across something, but not through it.